So before we get started here, just like to sort of thank everyone for joining us. We'll do a quick intro about who Canature is and who I am and that sort of thing before we get started. So in terms of who I am, this slide would work for me, please. Thank you. So my name's Tyler Gamble. I'm the General Manager of the Commercial Industrial Engineering Division for Canature Watergroup. I completed my engineering degrees both from McGill University and Dalhousie over the last decade or so. I've been working in the water industry since 2010, and in 2019, I was fortunate enough to be named one of Water Quality Products Making Waves people. So it was a group of people who are identified to be influencers in the industry who are under the age of 40. So it was kind of fun to be part of that, along with a bunch of other great individuals who were part of that. And then in terms of who Canature Watergroup is, so for those of you who aren't familiar with us, we're commercial and domestic and industrial, all sorts of groups, water conditioning manufacturing company. We have multiple locations where we manufacture our equipment out of, as you can sort of see on the map, 2 in Canada, 3 in the US, and then 1 in Mexico. And our whole drive behind who Canature Watergroup is over its various iterations over the last 50 years is to really provide our customers with innovative, high quality products and drive to be sort of an innovator within the industry with regards to efficiencies, whether it comes to water usage on RO systems, like our under-counter Hero system, or whether it comes to pushing the limits on what the salt settings can do within softeners and resin and that sort of thing, all with the idea that we want to provide the best value for the end user who is going to ultimately be the one using the equipment. Part of that value is having a great team to be able to support not only you when you're making your selections with regards to equipment, but then also helping your customers at the end of the day and your clients knowing that they've got the support that they may need down the road when it comes time to do, whether it's standard maintenance, whether it's time to do some troubleshooting because something isn't working quite right, or even just generic questions about how the system works. So that way your customers or even you yourself can get a better understanding of what it is that's going to be installed, how it's going to work, and how it's going to work in conjunction with everything else. So enough about all that. We'll get into the meat of today's presentation. So what we're really going to focus on today, as you can sort of tell by the cover, was that we're really going to be talking about commercial water softeners. So why are they used, where are they used, the conventional design, and then once we've covered those a little bit to understand sort of the history and why we're using them, then we're going to look into why or how ion exchange works. We'll take a look at the water softener meters quickly just to sort of understand how they work as well. And then once we've understood both of those options, then we're going to look at, okay, is there a better way to actually design a water softener so that way it better matches the systems that we're talking about and the buildings that we're talking about. So what I really want to try and focus on primarily today is I'm going to be focusing on commercial applications, and I'm going to be focusing on municipal water quality. Just so that way we can sort of rein in our focus on what exactly we're looking at, and I'll define what both of those mean later on. But if we're going to start, well, I won't be touching too much on high purity water and that sort of thing. Not that that's not something we can't discuss later on, but just in terms of this presentation, it's going to focus solely on the other options that I mentioned. So first of all, why are we using water softeners? It's probably the big thing that we need to understand first before we decide whether or not to install it. So water softeners use ion exchange to remove nuisance minerals like calcium, magnesium, iron, manganese, those sorts of things, and other cations if there are any in the water that we're worried about, and replace them with the desired cations to soften the water. Normally that desired cation or mineral is sodium. However, there are examples of other people using different minerals, potassium being the other one, where they're trying to put that in the water instead of, say, sodium. But sodium is far and away the most common one that we use in terms of the exchange that we want to make. So these nuisance minerals can cause things like scaling in pipes, and equipment and fixtures, like you can sort of see the picture on the bottom right there. That's some pretty heavy scale boiler tubes that obviously have not seen the proper pre-treatment and or chemicals applied to them. So part of that scaling and buildup can really shorten the lifespan of your equipment and or result in really high maintenance costs, a lot higher than probably you projected going forward. The nice thing about softened water as well is because all our minerals are removed and you don't have that scaling factor, is that our energy crease for water, for heating water, I should say, are far less, and that you don't have that scale buildup that provides an insulative layer against that heat transfer that you're trying to get into the water. Softened water, because of the way it works with soap and that sort of thing, or I should say the way that the calcium and magnesium works with the soap in the water, you need a lot less soap in order to achieve the same amount of cleaning power, to put it simply, with softened water compared to hard water. And then a couple other little things here. So spotting on dishes, glasswares, automobiles, that sort of thing. So if you're looking at things like hotels, car washes, and that sort of thing, softened water is going to rinse away better. And when it does rinse away, you're not going to leave those spots on the cars necessarily that you did before. And then one last little thing here in terms of if you're doing your own laundry on site at a hotel, or if you're running a laundromat, say, you're going to, by using softened water, I should say by using hard water, you're going to decrease the life of the linens and the clothing that you're trying to wash. So where are water softeners used? Well, I kind of hinted at it a little bit there, but just to sort of put a kind of bow on it, so to speak, is that really anywhere where you're encountering hard water is somewhere where you're going to want to put in a water softener. And hard water, as defined by the Water Quality Association, is anything above 10 grains, or actually no, it's above 5 grains anyway. Very hard water is considered 10 grains, but really anything above 5 is something that really we should be looking at. So places like hospitals, doctors' offices, and that sort of thing, they're going to be wanting to look at soft water. Schools, hotels, restaurants, any place where, like I had mentioned before, some of those impacts in terms of the equipment being mal-maintained, some of the aesthetic issues regarding spotting and just deterioration of your whatever it is you're trying to wash over time, anywhere where you're looking at those sort of options is where you want to try and put in a softener. And another area as well that you'd want to look at is pre-treatment for some of these heavy use fixtures or boilers or RO systems and that sort of thing. And one last point to bring up on in terms of where they're used, water quality really doesn't play into it too much. You can find hard water at any one of these sources, whether it's municipal well or surface water. Typically speaking, you're going to find less hard water with surface water than you would find with, say, well, but it's not that one sort of dictates the other. The best way to always figure that out is you always need to make sure to get a water quality report of whatever application it is that you're trying to work on. So now with regards to the softeners, in terms of how we approach how to soften the water. So we're gonna look at it from two sort of perspectives here. So the picture on the left here would be a large single or twin alternating system designed around the peak flow rate, and then on the right is going to be multiple smaller tanks or multiple tank system (MTS) that's going to use smaller tanks in order to try and match the flow rates a little bit better. So first we'll take a look at the option on the left, this large single or twin alternating, get a feeling for what that means. So with regards to conventional single tank design, it's usually approached as a one-size-fits-all flow rates approach. So usually you go, when you're designing these systems, you go and you'll define whatever it is your flow rate is that you want to try and match, whether it's a peak, critical, or maybe based on some sort of pressure drop, based on a service flow rate, whatever you have you. And then you may put two fiberglass tanks, as you can sort of see here, on the system if you need 24/7 water. So that way when one softener gets depleted, then it'll flip the operation side over to the second tank, and then that first tank that was the tank in service will then regenerate and then sit there and wait for the other tank to do its thing. Typically, these softeners operate at around a 10 or 15 pound per cubic foot salt setting. I'll get into later what that means and sort of what those numbers, how they impact what we're doing. And then in terms of your regeneration cycles, they're made standard across all water chemistry types. So we're not really concerned whether it's surface water with what could have some turbidity in it, or we're looking at municipal water, which is typically very clean compared to some of the other places, or somewhere in between. So in terms of the advantages that you're going to see with a conventional single tank design, you're looking at simple installation with minimal piping. There's only 1 or 2 tanks there, so there really isn't a whole lot to do in terms of plumbing. Simple operation and troubleshooting, meaning that you've only got the 1 tank there. So you always know whether or not that tank is either in service or regenerating. And then if you do need to do some troubleshooting, it's generally pretty easy to figure out which valve is not working properly or media bed or what have you, because there's only 1 or 2 systems there. For single tank options, these systems are generally inexpensive and they can fit into pretty tight spaces. But once again, that's for a single tank. The duplex option, you sort of have to figure that out whether or not it works within your footprint. And then with the high salt settings, as I've mentioned, that 10 or 15 pounds, you get a very high capacity per cubic foot, which means you get longer service run times, and you also get some low hardness slippage, which might be advantageous for what you need. However, some of the disadvantages that we'd be looking at is that, typically speaking, tanks are way oversized for what they actually need for commercial applications. The thing we're going to really hammer home here today is that softening resin has both a peak flow rate, which we've talked about a little bit, but they also have a minimum flow rate that we need to respect to make sure that the water is getting softened appropriately. During low flow events, these larger systems, larger single tank systems, generally speaking, have a much larger meter on there. And these larger meters aren't able to soften the water to the same accuracy or precision as a smaller flow meter. So that's also something that we'll dive into. And we'll also talk about something called hardness channeling, which is tied to the minimum flow rate of the softening resin. If you do have a single tank, you do need a dedicated time every day in when it's going to regenerate. Some areas that's not that big a deal, like say if it's a restaurant, that's more of a resto bar sort of thing where they've got the lunch hour, they've got supper hour, and then they go into the evening for drinks and that sort of thing. But then generally speaking, during the midnight hour or after midnight and that sort of thing, depending where you are, there's really no water usage to speak of, so they can regenerate. So a single tank system might work there. A lot of places that need 24/7 water, however, not necessarily the case. If you are used, single tanks will also be less efficient because you're always going to design with them in mind, saying, hey, I want to make sure I always have softened water, so I'm always going to design a little extra capacity in there based on my run times and my usage. So you're always going to be regenerating bed that still has capacity left. So you're going to be inefficient in that method. And then if you are in an application, lastly, where you do have water demand 24/7, but you only have room for a single, then you have to try and plan your times around, your regeneration times around, saying, hey, I need a 3-hour window here where we're not using much water, but during that time you are going to pass hard water. It's a matter of fact, and whether or not that's acceptable is a whole other question. And then obviously with a single tank or just a twin tank setup, you've got either no or low system redundancy, meaning that if something goes wrong, you don't have the ability really to be taking your time with a fix. You need parts and you need them now. So now that we've understood that, now we're going to get into some of the basics of softening and really how does it work. So first of all, we're going to look at the workhorse of the system really, and the part that does all our work when it comes to softening water is the ion exchange resin, how it works. So ion exchange beads provide places, if you read the actual spec sheets, they call them functional groups, where these nuisance minerals I've spoken about are exchanged with sodium. In the picture on the right here, we're showing a demineralization application where we actually have sodium being removed for protons, for hydrogen protons. If you sort of picture that those sodium ions are actually calcium or magnesium, then same sort of idea. However, one inaccuracy with this picture that I like to point out is sort of the way that this picture is shown here is that the cation exchange resins, so these guys in red here, are viewed more like marbles, impervious marbles that water goes around in between the beds, in between the beads, and then goes straight down to the distribution go up where you only have the exchange surface on the outside. And this is the way I actually thought of it for a long time, for a while too, before I started to educate myself on all this. What it actually looks like, these resin beads, they're not impervious marbles. They're more like spaghetti that's been stuck in a colander for too long after you've drained it. So you know when you sort of cook spaghetti and you drain it off and you leave it sit in the colander for say 10-15 minutes, and you try and pick it up, is you get the whole clump at the same time. Well, that's more what ion exchange beads look like when you really get down and close on them. And that's all of those strands of spaghetti have all those functional groups where we want to do those ion exchanges. And really what we want to try and do is we want to try and force the water through the beads. That's where the majority, if not 99+% of our exchange sites are, is on the inside of that bead, not on the outside. And so this is where we speak to hardness channeling a little bit. So when a softening system is sized appropriately, our hard water passes through that little green line there that I've shown, and it goes through the resin. And this is only one path that it can take, but you can sort of picture that the water will enter and exit at multiple random locations across the resin bead, meaning our entire resin bead is used evenly. And that means that as our resin beads are used evenly, as we continue to go down the depth of the bed, it also gets used evenly. So you're not worried about hardness bleeding through. However, when we don't force the water through the center of the resin, what ends up happening is that the water starts to go around it, and then you can sort of imagine this right now, is that only the exchange sites on the outside here are actually exchanged, but then you've got all of these thousands upon thousands of exchange sites in the middle of the resin that aren't being used. So your capacity isn't being used properly, which means you get hardness slipping through the resin bed faster than you had anticipated. So why does it do this? Why doesn't it just go through the resin bead normally? Well, in a word, lazy. Water is lazy. Water is like all of us. It has a point A that it wants to get to and a point B. And basically we're forcing it through the softener on the inlet side, and the water just wants to get to the outlet side. It doesn't care how it does it. It just wants to do it the quickest and easiest way possible. Well, the quickest and easy way possible is actually to go around the resin. And this is because of if you've taken any sort of fluid mechanics classes, it's because of the no slip condition, but I'll explain this a little bit better here. So if you haven't taken it, you can sort of picture when you've opened up a tap in your bathroom, kitchen, or wherever, and you've opened it up just a little bit. You see the water comes out in a nice clean stream. You don't hear all that twirling, swirling noise, whatever you want to call it. But it sort of comes out and then it sort of drops then down into the sink and then pools and then goes away. That's what laminar flow looks like. And the reason why it's called laminar flow is it's that the profile of the laminar flow looks like this within a pipe, in the sense that the pipe wall holds back some of that water because it's got some friction associated with it. Meanwhile, the middle of the pipe that's far away from the pipe wall and far away from any water molecules that are going to try and be held up, it's going to go the fastest. That works really well, but you can also make this water sort of deviate and do a lot of different things because you're not pushing it through fast enough. So what we actually want to see is more something like turbulent flow. And turbulent flow is when you open up that faucet again, full blast, and then you sort of hear that noise that you sort of associate with water coming out of a faucet, is that it's kind of got a swirling noise to it, sort of thing. And that's because that basically we're forcing so much water through it so fast that there's too much going on, is probably the best way to put it. And the water's going, I got to get moving here, and I got to get moving fast. And you get all these little things going on. The flow profile, while it looks a little messy up front here, is actually pretty flat across the front, in the sense that the velocity across almost the entire section of the pipe is the same. Well, now if we sort of take that concept and apply it to a resin bead, you can sort of picture that the resin bead is our pipe wall. And if you don't force it, it's going to go around it. It's not going to go through it, because there isn't anybody trying to push it from behind saying, hey, you got to go in here because I need to get through too. So one way to sort of think of it, of this concept, is kind of basically a city in the middle of nowhere. And I know about that because I'm basically from there, and that I live in Regina. Regina is a city of around 220, 230,000 people, and there's literally nothing but farmland around the city. So if you're trying to get across the city, the easiest thing to do is take these circumferential highways or ring roads, whatever you want to call them, and then basically go around town. So that way you can keep going through to the other side of the city, wherever it is you need to go. However, what we're trying to do is we want to try and force the cars to go through the city. In this case here, we want if you imagine the cars being water and the city being this resin bead, we want to try and force the cars through the city. Well, how do you do that? Well, you start to pile up the amount of traffic that's on that circumferential highway. Eventually, if this does get busy enough, it makes sense to go through the center of the city. And that's what we want to try and do. We want to try and force people through the center of the city, through the center of the resin. So that way they're using all of that available capacity, or in the case of the city, you're stopping at the Tim Hortons or wherever it is. So talked a lot about that, but what does channeling actually look like? And I really like this picture because it kind of takes all of what I said and puts it into context here. So the first thing that you'll notice is that our leading edge of our resin, so this line here where it first starts to change from this amber color to this green color, that leading edge is a lot more consistent than on this side here. If I back up here, you'll sort of notice that this here is pretty well clean in the sense that you can more or less draw a straight line here, versus this guy here, you can sort of see it starts to bleed up here, a little bit down here, and away we go across. So that sort of thing, right? Our leading edge is very well defined, and that's important because that leading edge being well defined ties into the controller, the valve, knowing when to regenerate. The other thing you'll notice is that it's a much darker leading edge as well. In this case here, normally all of this amber colored resin up here would also be this dark green color, but you'll notice that this leading edge is very well defined in its coloration as well, versus on the right side here, this is it's not very dark green at all. It sort of bleeds up the side of the wall here. It's very faint. So basically it means that we have no idea where the control valve thinks the leading edge is, which is a problem, because if the control valve thinks the leading edge is way up here, well, that's a problem because we have all this spent resin down here and we're very quickly going to bleed hardness. So that's what's important with regards to those minimum flow rates versus those higher flow rates. So let's talk about salt settings. Just briefly here, it's one table, pretty quick. So that's way it's easy to understand. So when I talked about those 10 or 15 pound salt settings, that means we're talking about when we do regeneration, how many pounds of salt per cubic foot of resin do we want to apply in order to regenerate and kick off all of those nuisance minerals and send them to drain. So most large softeners are operating around that 10 or 15 pound mark. So it means that their capacities are higher, their base leakage is lower, which is good, but our water usage and our salt usage is way up per regeneration. Versus if we get down to a 6 pound salt setting, yes, our capacity is reduced, but you sort of look at it here, 15 pounds down to 6 pounds is, I think, a 60% reduction, if I remember right. But we've only reduced our capacity by 30%, 33, right? That's not that big a deal in comparison. And that's because of the law of diminishing returns when it comes to actually regenerating the resin. In terms of the base leakage, 1.1 is fantastic, obviously. It's basically no hardness left in the water versus 5.5. But you'll notice that this 5.5 number, if you were to go and look up some manuals for what most equipment consider soft water to be, it's all less than 1 grain per gallon, which is about 17 parts per million or milligrams per liter. So this 5.5 is still well under that. So once again, for commercial applications, we're not really concerned about this being 5.5 versus this being 1.1, because that's what the equipment needs for it downstream of it, right? And then you'll also notice here that per regeneration, our water usage is a lot lower and our salt usage is a lot lower. So we'll sort of talk about how all that plays together later on in the example. So now when it comes to these flow meters, larger tanks need larger control valves because typically they have much higher flow rates going through them. So if it's a larger control valve, larger flow rates means we need a larger meter. The thing about flow meters is they don't actually measure flow rate. They measure the velocity in the pipe, which then gets interpreted into a flow, whether it's calculated or whatever. So the important thing to note here is that as you can sort of see all these points here is that as our flow meter gets larger, the flow rate which they can detect down to gets larger as well, to the point where when we have a 1-inch meter, we can be really accurate, around 0.7 gallons per minute, 3/4, whatever. Versus when we get up to 3-inch meter, then we've got that 7 gallon per minute mark, which is 10 times higher, but we've only increased our diameter of our pipe 3 times. That has to do with the whole area thing. But the big thing though, is that while these are the minimum flow rates in order to maintain the flow rate, because this is what you're going to find on spec sheets, typically speaking, once a flow meter stops, in order to get it moving again, you need about double these values. So that means now that this is 1.5 or 1.4, still not bad, but now this 3-inch meter needs 14 gallons per minute. That's like the equivalent of 10 toilets running, or whatever, or maybe 15 faucets, whatever it is. That's a lot of faucets online at once that need to be online in order for this system to be running, for this system to recognize flow and then calculate for it. Once again, gets to be a bit of a problem. So the big question about all this is there a better way? Now that we know all these things, we know some of the pitfalls of those larger softeners, where do we go from here? So why do we need a change? Well, these old design values that we're talking about, these peak flow rates, are still based on textbook values that are still pretty old. If you take the Hunter curve, for example, that a lot of people are probably familiar with on this call, in order to calculate your peak flow rates, that's still based on numbers from the 30s and the 40s at best. There are some newer versions of it out there, but generally speaking, they still oversize things quite drastically compared to what actually is being used. And everybody's kind of aware of that for the most part, but when you're using it to size pipes, if your pipe's a little bit bigger, and it means that the person on the 30th floor of your condo building isn't going to complain about low water pressure because their pipe is choked down too much, not a big deal. Problem is when you have other equipment in there that has a minimum flow rate, that's where it becomes a problem. And if you don't account for that minimum flow rate. So to that point, one size fits all never fits all flow rates. And that's what is the major problem with these single and twin alternating systems is that they're just based on that high peak flow rate. And those peak flow rates by definition are done for maybe a minute a day, 30 seconds, 10 seconds, whatever it is. There's still over 1,400 minutes left in the day that need to be accounted for in terms of your design. So that's something that needs to be considered. So what can we change? What do we have the ability to change when we're designing softeners? We can look at our tank size and quantity. We can look at our salt settings, and we can look at our regeneration cycle settings. And that'll help. These last two numbers will go and help those water efficiency things like we've stated. So, but the big thing is how are these going to impact performance? Well, let's get back to the basics here in terms of what do you need to know when you're talking about flow rates or talking about designing a softener. Well, first, we're just going to look at the big bold items here. We need to know the water chemistry. We need to know daily flow rate. We want to know what our flow rates are at any given time, and we want to know what the application is. Some things that aren't necessarily always looked at are things like the water source. Are we talking about municipal water? Are we talking about well water? If we're talking about well water, is it a dugout? Is it a 300-foot depth well? What are we saying here? Or is it a spring? Or maybe we sucking out of a pond that has canoers on it frequently, and then that intake pipe is going to get all filled up with turbidity. And that's actually a thing. I've run into that before, where somebody was having trouble with their softener, and it turns out every 6 months or so they would be all just filled with sand. because there's be some paddlers that would be going through a pond where it was close to the intake pipe. Next thing we want to look at are our flow rates, and we need to understand what is the minimum flow rate that we're willing to accept. Not that we need, because obviously it would be nice if it was 0, but it's never going to be 0. That's borderline impossible. So we just want to understand what is our minimum flow rate that we're willing to accept for the softeners, and then how do we manage that? And then lastly here, what's our application? So when I say what's our application is, are we talking about a commercial system where acceptable hardness is less than 17 parts per million or grain per gallon, depending where you're at in the world? Or is industrial high purity application where acceptable is roughly around a part? Maybe it's lower than that of hardness. All sort of depends. So when it comes to reducing salt consumption, because commercial equipment doesn't need the highest quality water in order to operate equipment effectively, we can reduce our salt setting and still get performance that we're okay with. If you remember that table I showed, we're talking about going from 1.1 parts per million of hardness to 17.1, or sorry, to 5.5, what am I saying? To 5.5. That's still well less than 17. So 6 pounds is probably fine. If you're going into another application, you need to review that again. Because we're going to be using less salt, that's less salt going down the drain into wastewater systems, into irrigation fields if the wastewater is used for irrigation, wherever it may be. Downside of it is, because we reduced our salt capacity or salt setting, we've reduced our capacity of our resin by 33% compared to the full 15 pounds. So that might end up increasing the number, well, will increase the number of regeneration, so we might end up using more water. Speak to that in a minute. So what do we know about reducing water consumption? Once again, is that we, in terms of our backwash times and that sort of thing, where municipal water is generally low in suspended solids. So backwash times can be reduced instead of that standard 12, 15 minutes, whatever it is you're currently using, but we can reduce it down to maybe 8, 7, 6 minutes, or maybe periodically we can get rid of it altogether. Maybe, sort of depends. But the big benefit is that we're going to be significantly reducing the water consumption of it all. So, responsive flow softeners. You might also know them by the name progressive flow, demand recall, demand flow. They all mean the same thing. I'm going to say responsive flow for, and you've probably heard me say it for this presentation. So what are they? Typically, we're talking about 3, 4, 5, 6 tanks that all are plumbed in parallel that are going to have softeners come online and offline based on the actual flow rate that's going through the softeners in any given moment. So why does it work better? Well, we're able to capture all those peak flow rates, and then we're also able to capture those low flow rates as well, because we'll bring the tanks online, we'll bring the tanks offline as needed. Because we have smaller tanks, we're able to have smaller control valves and smaller meters, meaning that we're able to meter more accurately, more precisely, and because our tanks are smaller and the number of cubic feet online at any given time is also smaller, our minimum flow rate for our system is smaller. And then a lot of people thinking like that install looks pretty complicated, must be worth quite a few bucks compared to the standard systems. Like, well, that is also one of those things that's not always the case, and we'll get into. So in terms of, once again, just to sort of go through this, and this is more of a visualization of what is going on here. You can sort of see the low flow rate requirements. We've got this one tank online. Say if there's a 5 gallon a minute going through this system, we've got one tank online, it's happy. Now we're going to get up to around that 50 gallon per minute mark, let's say, and then all of a sudden 3 of our tanks come online, maybe a 4th one, depending on our trip points that we've defined at which the softening system brings online and offline tanks. So in terms of the CapEx, because at the end of the day, if this was way expensive, people wouldn't use it, right? So with multiple tanks, you must have, that's a lot of valves, a lot of meters, a lot of everything, right? So it must be more expensive. Well, not necessarily the case. So in terms of your tank size, to look at one metric here, when you actually look at your tank size versus the amount of resin that you can put in any given tank, this actually ends up pretty much being a flat curve mean, you can look at the formula up here in terms of our linear regression. It's pretty much flat. You might as well call it flat. The reason for that is that basically a lot of people use more of these smaller tanks more often, so the equipment designed to make them is a lot more readily available. It's easier to ship these tanks because you can put a lot of them on the skid. So there's a lot of good things happening at these tank sizes here because of the fact that they're made so much more often. When you get into the bigger sizes here, shipping containers aren't necessarily designed to pack that many of these size tanks. The equipment that's needed to make them is more specialized, therefore more costly. It's a lot of these things. It's a lot of these economies of scale things that sort of build on each other that basically show that when you look at the cost per cubic foot for a tank, it's pretty well flat, regardless of whether you've got 14 inches or 63 inches. And that's a big difference in resin too. We're talking about 3 cubic feet versus 54, 53, somewhere in there. Anyway, some other factors that I can't analyze right now because it sort of depends on what's going on. The installation costs, that's going to vary site to site depending on what sort of materials you have, what sort of space you have. The footprint also obviously has a cost to it as well. And then the CapEx cost, some of the other materials there as well, depending on the material type, manufacturers, all those sorts of things. I use the tank one because it's pretty standard. It's a pretty easy one, but there are other things in here that influence our CapEx that we aren't able to address here. So will it be less expensive than conventional? Well, it depends. At the very least, more often than not, you're going to be around the same price. If not, even just slightly cheaper based on what we've seen out there, because those smaller valves are typically less expensive than the larger valves, even when you multiply them out. So operational advantages of our responsive flow system is you're able to capture all the high flow rates and the low flow rates. You meter more accurately, but does any of this actually matter in the real world? Well, we're going to get into a case study here. So this case study is from a hotel in Regina. You got 40 hotel rooms, 40 sinks. Each one of them has toilet, sink, and shower. You've got public washrooms, all with what they need, and then they also have the laundry machine down here as they're going to be doing their own on-site laundry. So in a perfect world, the hotel would be taking soft water, or demand for soft water would be 100% flat. That would make designing softeners very boring and very easy. I mean, boring is easy a lot of times in our industry. So, but what does it actually look like? This is actually a one-day scale, sort of take a one-day data log that we took from the actual hotel, showing its flow rate. So you can sort of see it goes up, it goes down, it goes everywhere in between throughout the day. So really, it's not just a flat sort of value. So in terms of our sizing zones, we've got a daily flow rate of 3,200 gallons. That's based on book values. As this was a brand new hotel, didn't have a water meter. A water meter would have been nice to understand what their daily flow is, but in this case here, we'll use book values. Regina municipal water is roughly 20 grains. Sometimes can be higher, sometimes lower, depends time of year. A lot of it does different things. Our peak flow calculation actually turns out to be 84 gallons, and I'll show you that in a minute why that's also important and relates back to a comment I made earlier. Because it's a hotel, you see that they require 24/7 soft water. We're also dealing with a commercial application, not super high, like the equipment that we need here doesn't need the highest quality of water. So let's compare two systems. Our conventional twin alternating 10 cubic foot tank, 2-inch valve, and then a responsive flow. We're going to use a quadplex 3 cubic foot tank with 1.25 inch valve. The minimum flow rates regards channeling are a lot higher than in the conventional one than on the responsive flow, and we'll show why that's important in a minute here. So in terms of designing for peak flow rates, which is what the conventional system uses, you'll notice here that our peak flow rates, you get a bit of a peak here in the morning around 40 and then another peak of around 50. That's a lot lower than the 84 than we had measured before. So that in itself is a problem. But you'll notice here that that only happens for maybe these peak times are only for about 2 hours of the day. and don't even come anywhere close to the peak we actually calculated. So number one, we're starting to over design our softener already. So then when we look at the whole profile, you'll notice that that initial system, that conventional system, is going to have trouble or not measure flow rates down here at all. And this is during prime business hours, 10 a.m. to 3 p.m., or I should say 10 a.m. and 3 p.m. And then also throughout all of the overnight hours, we're not going to get any measurements either. So that's quite a problem here, because now look where we had our peak flow rates, our calculated peak flow rate doesn't even show up on this chart, versus we've actually got channeling issues for about a quarter of the day. Not only channeling issues, but metering issues and everything that's associated with that. So that's a big problem with that conventional system. If we look at our responsive flow system, now we've got the minimum flow rates are well below, or not well below, but they're below anything that was measured at the hotel during that time. So that responsive flow unit is going to be able to capture all those flow rates, soften effectively, and not worry and not have the same problems that the conventional system did. So this next slide here, we've got an animation going once it loads. You'll notice our tanks on the left-hand side, responsive flow, system goes down evenly. As the flow rates increase, we're going to bring on our tanks online, eventually here once it hits 15, I believe. There it goes. So now we've brought our second tank online. It's going to eventually bring the third tank online as we go here. And here we go. With our traditional system, as you sort of see here, and this animation will loop back around. But notice how we've only ever had the one system online the entire time, regardless of what the flow rate is. So it means we're just using that capacity up as we go down. And you notice here when we are at our low flow rates here and we start, we've got channeling issues to start. So just picture that happening multiple times a day based on that previous sheet that I just showed you, that previous chart. So it gives you an idea that eventually all the channeling is going to result in hard water slipping, getting to those laundry machines where they're going to be seeing hard water, which means that they're going to have to use more soap or hotter water in order to clean their clothes effectively. They're going to be spotting on dishes, glassware, whatever. So it's one of those things that while it's a lot of times it's overlooked, it is really important to how you want your system to work when you design for it. So in terms of the water usage on either system, you notice here right away, big win for the responsive flow system when we look at our gallons used per cubic foot in terms of our regeneration water, 53 versus 36. However, as I've discussed before, our capacities are a lot lower. So how does that play out? Well, when we look at it normalized per 1,000 grains of hardness treated, there is actually a slight advantage to the twin alternating system compared to the responsive flow. However, we're talking about 0.04 of a gallon on almost 2 gallons. So we're talking about 2% difference in terms of water use on these two systems. There is another version where instead of a quadplex, we use a triplex, that actually this water usage flips on its head, and there's actually an advantage to the triplex system where it ends up saving about 20% more water than the twin alternating system does. So it's one of those things you always sort of want to try and balance what you're looking at. So in terms of some other numbers with regards to this system, our salt use per year is way down, as we sort of talked about. Our water usage is slightly up, but that's fine. But then you can look at here, our total annual savings ends up being just shy of $1,000, which is pretty good. But what does that mean as a number relative to the amount of OPEX costs that you would have normally used? Well, that's actually ends up being a saving of around 30% for this system. So while $1,000 or close to $1,000 here for this one water softener ends up sort of bringing back your ROI in a hurry, one softener versus the other. If you can imagine this 30.5% on a much larger system or multiple systems, I know some of you are probably working on projects out there where they have either the need for a much larger softener or many softeners throughout a hotel complex or that sort of thing, now that $1,000 can now become 2,000, 5,000, 10,000, depending on how much water and salt they're using. So this number here can really add up in a hurry just by adopting a different kind of softener and a different thinking towards softeners. So turn to the summary regarding responsive flow softeners. Our advantages: we've got multiple tanks, which means we get better flow coverage. We're able to soften down to the small flow rates all the way up to big flow rates. Same thing with those meters. We've got better accuracy and precision. Our system redundancy, which isn't something I really talked to, but it goes up because now if one softener goes down, not as big a deal because we still have 2, 3, 4, 5 tanks sitting there ready to go online. That sort of gives you some time in order to make those changes, those repairs that you need to. A lot of the times, as I spoke to, you get a CapEx reduction on the softening equipment itself. But now in terms of some of the disadvantages, a lot of these advantages I'm going to speak to are stuff that us as a manufacturer need to take on. So lapping of online tanks, meaning that in terms of your system needing tank softeners to regenerate, what ends up happening is that sometimes you might have 2 softeners that are basically having a race to see who finishes first. Well, at least with our programming, with Canature Watergroup's valves, you'll have minimum values that if 2 softening tanks are within a certain percentage of each other and so far down their capacity, well, they'll actually kick one softener on early to regenerate versus the other. So that way, you're never going to have that lapping scenario where you've got one softener sitting there waiting to regenerate. That potentially could be passing hard water if it needs to bring on multiple tanks. You can have footprint challenges when compared to single tanks. Single tanks, I mean, obviously there isn't much there. But you do have some flexibility in terms of, I've seen many installations where they've got brine tanks across the room, and then they've just run the brine lines a little further. They've kind of created a little hallway with softeners on one side, brine tanks on the other. There are a bunch of different ways to get around it. And a lot of these are a lot more flexible when you're talking about new construction. When you're talking about renovations, then you have to be a little bit more flexible with what you need to do. I mean, I've also heard scenarios where they've put brine tanks in the parking garage as well. So kind of have to do what you need to do. Increase programming complexity. Once again, that's something that the manufacturer needs to take on, that being us, to make sure that all of that works properly. And those are things that we test for ahead of time and make sure that the system works the way that it's intended to. In terms of installation costs, those also might increase, but once again, you've got smaller pipes now because you have smaller valves and that sort of thing, so there might be a balance there. So in conclusion, downside of conventional softeners, we've got they're typically based on peak flow rates, as we sort of addressed there. That's not a good thing to do. They have regeneration cycles that assume worst case scenario water, multiple day capacity, all those sorts of things that drive up and up and up the size of the softener, and then also the amount of salt that it used and potentially water as well. You've got large tanks, large meters, means that they don't handle those low flow rates well, so you're going to end up with hard channeling issues. With the responsive flow scenario, you can capture both the high flow rates and the low flow rates, which means you can work your butter zone, for lack of a better term, is a lot larger. Now you can do all those single-digit gallon per minute flow rates, and you can do those 100-gallon per minute flow rates all on the same system. You can't say that for the conventional system, those large single, twin outs, that sort of thing. Your smaller valves have smaller meters, so you're gonna be able to meter more accurately. So that way you know that you're regenerating when you need to. You won't have to go and monitor it and kick it into a early regeneration because you're bleeding hard water before you thought it was going to. You can reduce your salt settings based on your application needs. Now that's the big thing that a lot of people can do right now, even without a responsive flow system, but then just choose not to just because it's easy. Just sort of set and forget it, walk away. Well, there are a lot of cost savings to be had there. And then you can also, in order to reduce your backwash times, your backwash and rinse times based on your water quality. So that way you're not sending a lot of that clean water down the drain when you don't have to. So with that, I'd like to thank everybody for joining us today, and I'll open the floor to any questions that may have come through, and we'll go from there. Also, I'll unmute everybody. So that way, if you do want to ask a question here, feel free to, or once again, throw it into the chat. See, we don't have any questions just yet in the chat, so I'll leave that open here for a couple minutes. Give everybody a chance to sort of think about what they heard, if they have any other questions. Also, contact info is all there, so feel free to either reach out to me directly or call into our toll-free line and talk to any one of the individuals that I showed there on the second or third slide. I'll be able to help you with whatever application it is. And one other thing of note is that we are going to be running more of these webinars. So if you do have any ideas or for topics that you'd like to hear us talk about, then you can definitely send those in as well and go from there. So we do have a couple questions came in here. So first one here from Sven, and it says, any consideration when it's an existing building? Existing buildings, the biggest thing that you're going to have to take into account, there are some advantages and disadvantages. Disadvantages in that you have a fixed footprint. There's no way to sort of, or changing your footprint it can be very difficult. More often than not, these softeners are in mechanical rooms, big concrete walls do not move well. So in an existing building, you're sort of fixed to your footprint. However, you actually know, assuming that they've got proper metering and data logging and that sort of thing, you'll know exactly what your peak flow rates are, what your daily flow rates are. So you'll really be able to dial in what you want for a softener. So that is the nice thing about existing buildings. But when it comes to footprints, you've got challenges there, potentially. Not all the time. I've seen many renovations where they've ripped out old twin alternating softeners that were way oversized for what the building need, and we've gone in and put triplexes and quads in that exact same location where that other softener was. So it can be done. So Matt Paris, is there a sizing guide for progressive softeners? In a word, I'm going to say no, just because each application a lot of the times ends up having its own sort of idiosyncrasies you really want to try and account for. When we try and ask for those, and we don't always get that information, so generally speaking, we'll go by rule of thumb in terms with commercial applications. A lot of times softeners are sized solely on peak flow. The daily capacity doesn't actually end up factoring into the size of the softener at all. So we do have some rules of thumb for a certain pipe size for a certain softener, but that can depend on footprint and that sort of thing. So for example, 2-inch line, 80 gallons per minute is one that we get a lot of. So generally speaking, we'll use, I showed a quad here in this application to really drive down that minimum flow rate. But generally speaking, we'll advise of a triplex with slightly larger tanks. We're talking about going from 14-inch tanks to 18-inch tanks, which means our channeling flow rate is a little bit higher, goes from 3 to 5. But then space required for everything is a little bit lower. So generally speaking, it fits in a little bit better. But sizing guide it's not, what I sort of tried to speak to earlier was that there really isn't a one size fits all. So that's one of the important things to know, not just about progressive softeners in general, but really about any application you're running into. And that's one of those areas where give us a call, give us the application details, we'll walk you through what you need. From Ashwin, so if I understand correctly, the Hunter curve peak can't be relied upon to determine max design flow. What would be the alternative way of finding a peak flow? If I sort of came across that way, it wasn't intentional. The Hunter curve peak gives you a good idea of what the max can be. Generally speaking, in any application I've ever seen, the Hunter curve really overestimates what that peak flow rate is, which ends up driving a lot of other design decisions with respect to softeners that are ill-advised. With regards to making tanks too big, capacities are sort of shot through the roof and that sort of thing. If you reach out to IAPMO, they have developed a guide for condo type buildings, hotel, the basic that take into account the current low flow fixtures that most people use today. We use it on occasion, depending on the comfort level of our customer as to what they're using, and we've used it before and it's worked rather well. So we have really got good understanding there. So I would say reach out to IATMO and see what you're able to get from them. That if all else fails, use the Hunter, but just know that you're going to want to maybe make sure to really use a responsive flow system, because that's where the responsive flow system is nice, is that when you have those 3 and 4 and 5 tanks online, you're still able to capture those small flow rates, even if you've overestimated the peak. So Robert Schuster, who do you view as your largest competitors with commercial water softeners? How do your softeners compare in quality and functionality and cost to Marlowe? So Marlowe would be one of our competitors. Yep. We have other ones out there too. Generally speaking, anytime we've sort of gone up face to face with our competitors, feature for feature, dollar for dollar, all that sort of things, we match up very well. There isn't a scenario where a lot of the times people have stuck with other groups, whether it's other competitors simply due to comfort. It's what they know, it's what the person knows, it's what they're used to, whatever it is. So we're really trying to challenge that, whether it's just by thinking about softeners differently or giving us a chance on a few quotes every now and then. That's really the important part that we want to try to address here. So maybe this is a conversation that you and I can take offline here. So feel free to scribble down my email there or my phone number and give me a shout later on, and we can speak to those sort of details then. With that, I don't see any other questions in the chat. So unless somebody wants to grab the mic, give her a go. Give that a second here. Sounds like crickets. So once again, thank you everyone for joining us. If you have any further questions at all, like I said, feel free to reach out to me directly. Feel free to reach out to our toll-free line and chat with any one of our commercial engineering department people there. And hopefully we can talk to you again soon. Thanks very much.